In this video, we're going to talk about elementary row operations in row echelon form. Now, when we solve a system of linear equations using Gaussian elimination, all the action is really on the coefficients of the variables. Matrices can be used to record the coefficients as we go through the steps of the Gaussian elimination process. We're going to illustrate this with the system of example 2a. So example 2a, you should remember, is x minus 2y plus z equals 7, 3x minus 5y plus z equals 14, 2x minus 2y minus z equals 3. Now, the augmented matrix of this system of equations only uses the coefficients or the numbers in front of the variables in each equation. So x minus 2y plus z equals 7 turns into 1 minus 2 plus 1 and then 1 and a 7. Goes through the same thing for both the other equations. Now, the entries in the last column are the numbers on the right-hand side of the equations. For the record, though, the coefficient matrix of this system is 1, negative 2, 1, 3, negative 5, 1, 2, negative 2, negative 1. Those are the entries, the coefficients of the variables. We use this matrix to solve certain linear systems later in this section. We're going to use the coefficient matrix to solve systems using the inverse method. So we're going to use inverse matrices for this. Now, as we repeat the Gaussian elimination process using example 2, we're going to record the corresponding action of the augmented matrix. So as you can see here, the first thing what we need to do is get rid of the x value or the x coefficient in the second row. So we're going to multiply the first row by negative 3 and add the results of equation 2, replacing equation 2. All this stuff happens and we get down to z equals 3. Once we get down to z equals 3, that's considered row echelon form. Row echelon form starts with the main diagonals being 1, and the rest underneath the main diagonal 1 are all zeros. Now, a matrix is in row echelon form. I'm reading the definition here. If the following conditions are satisfied: rows consisting entirely of zeros, if there are any, occur at the bottom of the matrix. The first entry in any row with non-zero entries is 1. The column subscript of the leading 1 entries increases as the row subscript increases. So in the first row, the first entry is going to be 1. In the second row, the first entry will be 0. Second entry will be 1. And in the third row, the first and second entries will be 0. The third entry will be a 1. Now again, our goal is to take a system of equations, write the corresponding augmented matrix, and transform it to row echelon form without carrying along the equations. From there, we can read off the solutions to the system fairly easily. Now, the operations that we use to transform a linear system to equivalent triangular form correspond to elementary row operations of the corresponding augmented matrix of the linear system. We've already seen this. We're just using it with matrices. Again, we can interchange any two rows, multiply all the elements of a row by a non-zero real number, and add a multiple of 1 to another row. Let's do that with example 4. First things first, we need to transform example A into an augmented matrix. So 1, negative 1, 2, negative 3, 2, 1, negative 1, 0, negative 1, 2, negative 3, 7. That's the first thing we need to do. Now, generally the way you use this and transform these rows is to get rid of the second, third, first entry. Second and third rows, first entry. Now, we do that. The row that we want to change, we put an arrow next to it. Now, because the first entry is 2, I want to go negative 2 times the first row plus the second row. The first row is not going to change here. The second row is going to change. So negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times negative 1 is 2, plus 1 is 3. Negative 2 times 2 is negative 4. Minus 1 is negative 5. Negative 2 times negative 3 is 6. Plus 0 is 6. Now in our third row, you should see that we have a 1 and a negative 1. So because those are opposite, we can just add row 1 and row 3. 1 plus negative 1 is 0. Negative 1 plus 2 is 1. 2 plus negative 3 is negative 1. And negative 3 plus 7 is 4. What we can do now, in order to make this easier, we can transpose the second and third row. Now, it's not just the 4 to 6, that's the row. So let's rewrite the row. Like so. So now we have the start of row-echelon form. What we want to do next, we want to get rid of this 3 right here. So I'm going to multiply my second row by, let's try that again. I'm going to multiply my second row by negative 3 and add that to row 3. Again, my top row is not going to change. My second row is not going to change. My third row does change. 0 times negative 3 plus 0 is still 0. 1 times negative 3 is negative 3 plus 3 is 0. Negative 3 times negative 1 is 3 minus 5 is negative 2. Negative 3 times 4 is negative 12, plus 6 is negative 6. Now what we can do with our third row here, I can divide my third row by negative 2. By dividing that third row by negative 2, I'm going to make that third row a 1 and a 3. Negative 2 divided by negative 2 is 1. Negative 6 divided by negative 2 is 3. Now, this matrix is in row-echelon form. We can easily create equations to help solve this. From this equation here, we know z, not x, z is equal to 3. Y minus z is equal to 4. And x minus y plus 2z is equal to negative 3. This should be nice and easy. So y minus 3 equals 4, which means y will equal 7. And in the top equation, x minus 7 plus 2 times 3 does equal negative 3. Negative 7 plus 6 is negative 1, which means x will equal negative 2. So our answer to this system is negative 2, 7, 3.